Hi, welcome to the first functions tutorial titled What is a function? In today's tutorial, we are going to be defining a function and becoming more well acquainted with functions. In terms of what you need to know to progress with this section, you need to be familiar with your grade 10 work. You also need to have gone through the section I've included called Converting Words to Numbers. I'd also recommend that you first tackle the entire algebra section before moving on with this section. We will begin by looking at a basic definition of functions. A function is the graphical depiction of the relationship that exists between two variables, that is, the dependent and independent variables. The dependent variable, usually denoted as y, is the variable that has a value or values depending on the value or values of the independent variables. The independent variable is the variable that may hold any value irrespective of any other values. Stated differently, its value is not influenced by any of the other variables. Let us use an example to illustrate all of this. You run a company that manufactures pool covers. You determine that for every 10 pools, you will sell 3 pool covers. Is the number of built pools dependent on the number of pool covers? No. Hence, in this example, the number of pools will be referred to as the independent variable, as the number of pool covers does not influence the number of pools that exist. Does the number of pool covers you sell depend on the number of pools? Yes, because as there are more pools, you will sell proportionately more pool covers. Hence, the number of pool covers is dependent on the independent number of pools. Our equation looks like this. 3y is equals to 10x, or y is equals to 10 over 3x, where x is the number of pools and y is the number of pool covers. If we try and sketch the information, let us start by using a table. Let x be the number of pools and y the number of pool covers. When x is 0, the number of pool covers sold will be 0. When we have 10 pools, we will sell 3 pool covers. 20 pools, 6 pool covers. 30 pools, 9 pool covers, and 40 pools, 12 pool covers. If we take all of this information and we sketch it onto a graph, it will look like this. This is essentially a function. Let us use this example and expand on it further. Imagine at the start of the year, you have a contract to supply the government with 5 pool covers. Is this going to drastically change the shape of your graph? No. All it means is that at the start of the year, before you count the number of pools, i.e. when x is equals to 0, you have already sold 5 pool covers. That means that y is equals to 5 when x is equals to 0. This is going to shift our graph slightly. Let us look at how it affects the table. X being the number of pools, when that is 0, y is equals to 5 as opposed to the previous table which was 0, 0. When the number of pools is 10, the number of pool covers we sell is going to be 8. The reason it's 8 is because 3 pool covers for the 10 pools plus the 5 pool covers already sold. When X is 20, we will sell 11 pool covers. When X is 30, we will sell 14 covers. And when X is 40, we will sell 17 pool covers. Looking at the graph, it looks like this. Now let us bring on the graph from the previous example. Notice that it's just shifted upward. I want you to now have a go at plotting the following graphs. In the first 5, I have included the expression and a bit of the table, and I want you to first complete the table and then sketch the graph. In the next 5, I have only given you the expression. You choose which table you want to use, if at all, and then sketch the graph. The first function I gave you to do was f of x is equal to 4x plus 3. The accompanying table looked like this. Let us fill in the table first. If I substitute negative 3 into that will become 4 times negative 3 is negative 12 plus 3 is negative 9. The next one will be negative 5. 4 times negative 2 is negative 8 plus 3 is negative 5. 4 times negative 1 is negative 4 plus 3 is negative 1. 0 times 4 is 0 plus 3 is 3. 1 times 4 is 4 plus 3 is 7. 2 times 4 is 8 plus 3 is 11. And then 15. Let us sketch all of these points in. First point, x value is equal to negative 3. Let's put that negative 3 over there. Negative 3 and the accompanying y value is negative 9. So that's negative 2, negative 4, 6, 8, negative 9. So the first value or the first dot set of coordinates are going to be over there. The next ones is at negative 2 and negative 5. 2, 4, 5 is over there. Negative 2 and negative 5 is over there. The next set is at negative 1, negative 1, so that's over there. The next set is at x is equal to 0, y is equal to positive 3, so it's going to be over there. 1 and 7, x is equal to 1, y is going to equal 7, 2, 4, 6, 7. X is equal to 2, y is equal to 11, 2 and 11. The next one is at 3 and 15, that's 3 over there, and 2, 4, 6, 8, 10, 12, 14, 16, so 15 is over there, so it's going to be somewhere over there. I didn't draw it very accurately, but if we join these dots, and they should be joined fairly accurately, and yes they do, that will give us the function f of x. Always label your graph. You don't need to write the whole equation, just say that you have drawn f of x. The next one I gave you was g of x is equal to negative 3x plus 1. Notice that I gave you a slightly smaller table for this one. Two reasons for that. One, I want you to start getting used to drawing graphs without tables, so we're going to phase it out in the next few examples. And the other reason behind that was that I didn't want to do such long tables. Negative 3, the first x value we substitute in was negative 2. Negative 2 times negative 3 is positive 6, plus 1 is 7. Negative 1 in there gives us 3 plus 1, which is 4. 0 in there gives us 0 plus 1, which is 1. 1 multiplied in gives us negative 3 plus 1, which is negative 2. The next one we substituted in is 2. 2 times negative 3 is negative 6, plus 1, which is negative 5. I'm going to now sketch that. X value of negative 2. Let's choose that as negative 2. X value of negative 2, Y value of positive 7. 1, 2, 3, 4, 5, 6. So 7 is going to be somewhere over there. So our first point is there. Next point, negative 1 and 4. Negative 1 and 4. Next point, 0 and 1. It's over there. Next point, 1 and negative 2. 1, negative 2. Next point, 2 and 5. 2 and negative 5, which is over there. If I join that up, obviously, like I said before, my graphs are not very accurate. I just sort of did a more or less type of thing. But I joined that up. That also gives me a straight line, and that's the graph g of x. Number 3 read, h of x is equal to 3x plus 5. For this one here, I only gave you a small table with an x value of 0 and a y value, or an h of x value of 0, and I wanted you to find the corresponding values. When x is equal to 0, that becomes 3 times 0 is 0 plus 5, which is positive 5. When h of x is equal to 0, to get my corresponding x value, I'm going to say h of x is equal to 0. That means that 3x plus 5 is equal to 0. 3x is equal to negative 5. X is equal to negative 5 over 3. Now I can sketch it. When x is equal to 0, that's that line over there. Y is equal to 5. Let's put that over there. When x is equal to negative 5 over 3, which is somewhere over here, let's move that a little bit up, somewhere over there, y is equal to 0, so that's that line over there. So that's that set of coordinates. That means that my graph is going to look like this. And this is the graph h of x. Because it's a straight line, it's x to the power 1. Gradient times x to the power 1. Because it's a straight line, I only needed 2 points. These 2 points that I got are known as my intercepts. This is my y-intercept when x is equal to 0, and this is my x-intercept when y is equal to 0. Number 4 read, j of x is equal to 3 over x. And I wanted you to start by completing this table. When x is equal to negative 6, j of x is going to equal 3 over negative 6, which is the same as negative 1 over 2. When x is equal to negative 3, it's 3 over negative 3, which is negative 1. When x is equal to negative 1, it's going to be 3 divided by negative 1, which is negative 3. When x is equal to 0, denominator equal to 0, it can never. Hence that line does not exist, or that point does not exist. When x is equal to 1, j of x is going to equal 3 over 1, which is 3. 1 when x is equal to 3, and a half when x is equal to 6. Let us put these points in. When x is equal to negative 6, that's 1, 2, 3, 4, 5, 6, negative 6 over here. When x is negative 6, y, or j of x, is going to equal negative a half. So that's going to be over there. When x is negative 3, that's over there. Y is going to equal negative 1. When x is equal to negative 1, y is going to equal negative 3. When x is equal to 0, there's no solution. When x is equal to 1, that's over there, y is going to equal 3, 3 and 1, so that's 3, and 1 and 6 and a half. 6 and the y value is a half. Look at the shape of this graph here. Notice that it carries on in this direction. As my x value increases positively, my y value is going to decrease, but it's never going to be 0. It's going to approach 0. And similarly, as my x value decreases, as it becomes 0.00 something, my y value increases, but my x value never becomes 0. That means that for this graph, I have two asymptotes, or rather two restrictions. The one says that x cannot equal 0. That's basically my y-axis, that's that line over there. The other one says that y cannot equal 0, and that's the other asymptote, and that lies over there. These are called restrictions in algebra. When we move on to functions or onto graphs, these are called asymptotes. They are the same thing. Put arrows indicating that it moves in both directions, and please label it. Number 5. K of x is equal to 2 to the power x. When x is equal to -3, that's 2 to the power -3, which is the same as 1 over 8, or 1 over 2 to the positive 3, which is 8. 2 to the -2 will equal 1 over 4. 2 to the -2 to the -1 will equal 1 over 2. 2 to the power 0 is 1. Anything to the power 0 is always 1. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. Let us sketch this. -3, that's over here, and positive, these are our positive y values. -3 and positive 1 over 8 is going to be very, very close to our axis. -2 and 1 over 4 is going to be just a little bit higher than that. -1.5, also just slightly higher than that. Let's just make this one a bit lower. X is equal to 0, y is equal to 1. X is equal to 1, y is equal to 2. X is equal to 2, y is equal to 4. X is equal to 3, y is equal to 8. So that's way up here. Now let's look at the shape of this graph. If I join these dots, notice that it's going to carry on in both directions. It's going to sort of carry on curving upward, and it's going to carry on down here. As x becomes greater negative, it's just going to go closer and closer to the x-axis, but it's never going to touch it, which means that our asymptote is the line y is equal to 0. Y cannot ever equal 0, because 2 to the power x can never equal 0, or rather is always greater than or equal to 0. Hence our only asymptote is y cannot equal 0. Notice what happens as x starts to increase. The graph increases exponentially. This is called an exponential function. With an asymptote y is equal to 0, also keep in mind that it will, at x is equal to 0, it will always cross the y-axis at y is equal to positive 1. From number 6 onward, I gave you the function, but I did not give you a table to complete. Looking at this function, a of x is equal to 2x minus 1. we can very quickly say that this is a straight line graph. Reason it's a straight line graph, we've got a gradient, m, which is constant, and we've got x to the power 1. X is not part of the exponent, nor is it part of the denominator, hence this is a straight line. I'm not going to use a table, I'm just going to sketch this as is. I'm firstly going to start with my x-intercept, and that happens when y is equal to 0. That means that 2x minus 1 is equal to 0, 2x is equal to 1, x is equal to 1 over 2. So when y is equal to 0, x is equal to a half, positive a half. Let's put that over there. When y is 0, that's that line over there, x is equal to positive a half. The x-intercept happens when, the y-intercept happens when x is equal to 0. That means that y is equal to 2 times 0 minus 1, which is equal to negative 1. X is equal to 0, y is equal to negative 1. Now all I do is take my ruler and join the dots. And that's the graph A of x. Number 7, read B of x is equal to negative 2x plus 3. Again, because it's x to the exponent 1, x is not part of the exponent, nor is it part of the fraction. This here is a straight line graph. Start off by saying when x is equal to 0, y is going to equal positive 3. And when y is equal to 0, negative 2x is equal to negative 3. Remember, we're saying negative 2x plus 3 is equal to 0. That means that negative 2x is equal to negative 3. X is equal to negative 3 over negative 2, which is positive 3 over 2, which is going to be somewhere over here. And then I join it up because I know that it's a straight line graph. And that is B of x. Notice how straightforward and easy the straight line graph becomes as we progress on. Remember that we can only do this intercept method if it is a straight line graph. Make sure that you know it's a straight line graph before you do this. The next one we're looking at is C of x is equal to 4 to the power x. Now, unlike the previous few examples, this is not a straight line graph. This is an exponential graph. I'm not going to draw this using the table method though. Think about it. We know that our exponential graph looks like that, always. And it always cuts the y-axis at 1, provided there isn't anything else added on here. So we know that our graph is going to look something like this, and it's going to cut it at 1. Do we need to put any other information in? Not really. We can just call this C of x, and there's our graph drawn. If you want to, you can put in another point along the graph. Let's choose, for example, the point x is equal to 4. That means our y value, our x value is 4. Our y value will be 4 to the power 4, which is the same as 2 to the power 8, which is 256. Notice that doing it this method is a lot easier than the table method, simply because imagine how big our axis would have to be if we had to do a table method of just 1, 2, and 3. 4 to the power 3 is 128. Draw your graph like that. That's the exponential graph. The reason it's called the exponential graph is because the x value, the independent variable, is part of the exponent. Number 9 read D of x is equal to 4 to the power negative x. Now think about this one. when x is equal to 0, y is going to equal 1, right? That's fine. It's still an exponential graph. It cuts it at 1. That's cool. Problem. When x is equal to, say for example, 1, y is going to equal 4 to the minus 1, which is 1 over 4. When x is equal to negative 1, negative 1 times a negative is positive 1. 4 to the power 1 is 4. So notice something, that our new graph is going to be sketched sort of opposite to the previous graph, or rather inverted around the y-axis. We'll go through that later on when we look at transformations. Number 10. E of x is equal to 1 over 2x. Now notice something, that the independent variable x is part of our denominator in the fraction, which means that it's not a straight line function. We also know that it's not an exponential function. This is called a fraction function. I call it a fraction function. The technical fancy name is called a hyperbola. Now you'll remember from an example we did a few examples ago that the fraction or the hyperbola graph looked something like that. Again, do I need to do the table method to sketch it? No. I know that my graph is going to follow that pattern over there, with x cannot equal 0, hence y cannot equal 0, my two asymptotes, and the graph continues in that direction, and that's E of x. You only need to label one of them. If you want to, again, you can choose a point to plug in. Let's choose a point of, let's say x is equal to 2. If x is equal to 2, y is going to equal 1 over 2 times 2, which is 4, so it's 1 over 4. Obviously my graph is not very accurate, but you can just plug that, you can just put a point in just to indicate what's happening. Now I want you to have a go at the following. I've given you the expression and the accompanying graph, and for each one I want you to come up with a scenario that would possibly follow that in real life. Now for this next exercise, I gave you functions and I asked you to choose a scenario that could possibly fit the function. Now remember, you are probably not going to give the same scenario that I am going to give. There are an infinite amount of scenarios, possible scenarios that could fit each function. So I'm just giving you an example of an answer. The first one, g of x is equal to 2 over 13x plus 9. The next one, h of x is equal to 6 to the power x minus 240. The next one read L of x is equal to 1240 divided by x. Not too bad, is it? All that a function is the graphical depiction of the relationship between two different variables. That definition might have sounded a bit foreign at the start of this tutorial, but it became more clear as we progressed through it. In the next few tutorials, we will be looking at the linear relationship, that is the straight line. We'll be looking at the parabola, the exponential graph, the log graph, as well as the hyperbola. Before we move on to that, I want you to go through the exercise that I've left for you in the workbook.